Hello, math fans. I'm going to talk a little bit about triple integrals, do some visuals, go through an old quiz. If you would like to practice this, there's some examples there. You can see there's this example. I'd like you to try on your own. And I think it's a good exercise to try to set it up not just in 3 ways. I allowed my students to find any 3 correct ways. I would encourage you to try to set it up in all 6 ways. And I find this pretty helpful to start with pretty simple functions and do it in all 6 ways. Now, the main reason I'm making this video is because I made a video asking students for things they would like me to cover. And someone asked about Math 224. And I suspect it's a former student. I can't tell based off of the name. And I really appreciate your question. And since you were the first to ask, I wanted to hammer home one of these ideas. I have to admit that 224 is the course I've taught the least. The last time the department let me teach it was in 2013. I've asked for it many times, but they always have other bigger classes for me to teach. But I want to use this as an opportunity to show you how you can use my materials, because I won't be able to make a lot of 224 materials in the near future, but I did make a lot of stuff. Now, this was a time before, so I will do this question in a second, but I think this is even more valuable. Okay, so let's say you're struggling in Math 224. What you would do is you would go to my link here. Now, ignore the fact that it says 324 because the number just changed. When I taught this course, I tried to make a review sheet to go with every lecture. If you're willing to read, I don't have videos here, but if you're willing to read, and unfortunately this was before we posted lecture notes, this is a time of the past. But if you're just willing to work a little bit here, and again, if I ever get to teach this class again, I'll clean this up. But I want to show you how you can use it. So I have classic examples of triple integrals. I have a bunch of stuff here. But what I would do is, so you can see I have triple integral practice. I would click on a couple of these review sheets and go, okay, he's talking about this a little bit. Here's this practice sheet. Ooh, there's a little setup. Let's grab that. And I'm kind of doing this for myself. I remember how to do this, but let's grab it. And you can come back here and say, all right, Dr. Lovelace is suggesting a routine to do these problems. Maybe I can use that as a starting point to think through this. Okay, so let's read that and talk about it. So we're going to write down all the boundary conditions, because typically what happens in these questions, and this also happens in Math 126, is people feel overwhelmed. It's just a bunch of equations. So let's just write down what they are. And I'll grab the things. In doing this, I'll review a couple other things. But the boundaries are x equals 0, y equals 0, 2x plus y equals 6, z equals 0, and z equals the square root of x. Even just writing those, you gain some information. I mentioned trying to visualize in 3D, but if you sort of do several of these examples, you realize you don't have to do that much visualization. Already I see a few things. I mean, there are 2 x's, there are 2 y's, there are 3 x's. That kind of draws my attention. So you can even just do a variable count. 3 x's kind of suggests, and the way I used to teach students is we're going to make a choice for the innermost variable. After you make that choice, it becomes a 2-variable problem, and you're just going to use Math 126 ideas. So you sort of read through it, you've done some examples. Let's see if I can polish it up for you a little bit. And any time in the problem, you might want to do some intersection. So I talk here about find the intersecting curves. And there's several. So this is why the problem can be sort of large. But let's start simply. If you wanted to say, when do these 2 things intersect? This is just collecting information before I try to visualize or anything. I would get x equals 3. So that's going to be important in the problem in some way. And you can think of that this way. It doesn't have to, I mean, the moment we get in 3D, we start to lose people. I'm not good at visualizing in 3D, but I've learned to process my thinking. So y equals 0 is all the points on this side. Just some general things, and then we'll go through the process. And I'll go through all 6 ways. We'll end the video with that, but I'll say a few things along the way. So here we have y equals 0. Here we had this other thing, which was a line extended up. It intersects here at x equals 3. So that curve is one of the boundaries where the different sides meet. You can think of it as, sometimes one of these might just be a boundary itself, but you're going to have a bunch of places where the surfaces meet. If that's scary to you, look around the room you're in right now. There's probably a wall in front of you and there's probably a wall to your left. Where do they meet? They meet to form a line. That's what we're doing when we're finding these intersections. Now, I kept things kind of simple because that could get really messy. But other things, like when does 1 intersect with 5? Well, that would be when z equals the square root of 1. So that's 1 and 5 together. There aren't very many intersections in this one to really have to think about very much. When x is 1, y is 4. Okay, so I'm not going to go through and solve for every single one, and I'm not necessarily encouraging you to do that. As things get more complicated, you'd have to find the intersections, find where the edges are. Okay, so you have a few choices about what it can be. And I always like to think of it this way. We're either going to do the problem as a top-bottom problem, meaning we're going to think in terms of z on the inside. And in this case, when I look at the problem, that suggests that might be a good idea because I only have 2 z's that are suggested. One of the z's is z equals 0, which is just the ground. And the other z is z equals the square root of x, which you can graph in 2D and extend. We call it a cylinder, for those of you that took Math 126 with me. It's that square. So if you don't know what the square root looks like, it looks like this, but it's in the xz plane, and then it just extends out. So I can see already that that's going to be a successful approach. What I mean by that is I already see that this is something I can do to describe the solid. And the moment I've done that, the rest of the problem becomes a typical double integral problem. And what you do there is you're going to graph everything that remains after your intersections that has an x and a y. So at that moment, we switch over to Math 126, which I could review in just a moment. Okay? So I think of it this way. You choose the innermost variable. Honestly, you can choose anything, but some choices are going to be easier than others. And then you draw the 2D region and you do Math 126. So before we come back and do that, let's talk about Math 126 for a second, because that's often where the confusion is. Okay, so here we go. This is an example from my Math 126 course. I have students draw that region. We do this in class. I think that most of the time when I do this in class, it takes students all wander around, and I think about 60% of the class draws the correct picture, and the rest don't. So I know there's major challenges here. You need to draw y equals x squared, that parabola, and a line. It doesn't mention anything else, so you don't use any of the axes. So I would encourage you to stop and draw that and describe it. So this is just a 2D problem. Here is this region. I'm going to get rid of everything else for a moment. And this is a picture from that lecture. This is I do this with my students. There's that region. So you can see the parabola on the bottom. You can see the line. My students that take Math 126, I show them that picture and I make them immediately tell me which variable it is. Do we want to use x or do we want to use y? If you're in Math 224 and you don't know immediately looking at that whether you want to use x or y, that's something we need to fix. It's not hard to fix, but it's something we need to fix. In both work, but let me show you a picture here. So first I'm going to show you if you do it in terms of x. And you can ignore the height of that. Let's just pretend this is 2D for a second and see what happens. So we're going to say, I would like to increase and decrease x. As I increase and decrease x, I think of this as mowing the lawn is what I tell my students. I'm going to start on the left. I'm going to tell a person, I want you to start at -1. That's on the far left. And I'm going to shift over a little bit. And when you get to -0.5, I don't want you to turn on the mower until you get to the edge of the grass. When's that going to happen? That's going to happen when you get to x squared. And then you're going to keep mowing until you get to the line. And that works the whole way. Notice it doesn't ever change. And that's why we want to use x. So we want to do it in terms of x. And if you've taken Math 126, we say for every x from -1 to 3, those are those intersections, I want to go from this on the bottom to this on the top. All right? That's that piece. Okay. If I try to do it in terms of y, there's a problem. It switches. Let me show you. Let's do this one first. Oh, sorry. That's blue. All right. So when y is beginning out, I'm still in Math 126, but this sort of highlights the challenge of triple integrals. Is if you don't know your Math 126, is going to be hard. There's a problem that happens, and you can see it happened right there. The pattern changed. It's no longer between those. Now the pattern was correct back down here at the beginning, but it wasn't correct when we switched. And I tell students, easy to see, the left side changed. And you can see that from the beginning. The top and bottom never change, so it's nice to use x. The left and right do change, so it's not nice to do it in terms of y. That's the number one thing I try to tell students in Math 126. Notice here, so then this is the new pattern once you get past there. So we had to split that into two problems. So if you don't know that, or if you've forgotten it, I'll pull this up a little bit. Let's go to my website. We'll go to Math 126. We'll go to my old lecture notes. You could review that. You could say, I'm going to go to section 15.2, what that's from. Here's where I talk about describing regions and top, bottom, left, right. I do several examples. There we go. We need to understand top, bottom, left, right. I have practice quizzes on this. I have one where I go through in lots of detail here. You can do that. It's not too bad. Okay, so now let's go to the quiz. So we're going to go to this quiz, and we're going to try to deal with the issue. And I'm going to erase now, and let's go and let's attack this problem. Okay. And hopefully you've stopped and tried on your own. Sorry that the video's gotten too long. I hadn't really planned carefully for this. Just wanted to give that student a response because I so appreciate you giving me some feedback. Okay, so now we've chosen to use z on the inside. The next thing I do, so step 1, choose your inner bounds. And you really can choose anything you want. Step 2, draw these axes. And it's going to be the remaining variables. Step 3, draw any xy boundaries. Now in this case, they give me x equals 1, done. Y equals 0, done. And this line. Now this line is 2x plus y equals 6, which can be written in a few different ways. And we need to be comfortable rearranging. Those are skills from that course. I would always plug in a few points, but in particular, just to illustrate the issue, the intersections are definitely going to be important. So when I plugged in a 1, we already did this before. When I plugged in a 1, I got y was 4. So 4 is going to be important, 1 comma 4. And when I plug in y equals 0, I got x is 3. So 3 is going to be important, 3 comma 0. And then I have this point, 1 comma 0, and I have this region. Done. After you do a few of these, you start to see the routine. Choose your inner bound, draw your region, done. Describe your region. Now, here's where I'll give my recap of Math 126. I tell students you can describe the region either way, and there's a certain process I think everybody should do, and this goes for Math 125, Math 126, Math 224, is you're going to label a side. You're either going to label this x or you're going to label this y. This is what I say in Math 126. And then you're going to try to find a pattern based off of x, this way or that way. And they're both perfectly fine. And here's how you do it. You say, well, what's the biggest and smallest x can be? Well, it's 1 to 3. It's going to be integral from 1 to 3. And then based off of x, what are the bounds for y? So based off of x, what are the bounds for y? Well, it's bottom and top. You need to mow the lawn. So it should be in terms of x. That's why I like to label x first, because too many people mess up their variables. And so you label x, and you say, what's the biggest and smallest x can be? And then you label these in terms of x. So this is 6 minus 2x. This is 0. This is why I can do this so many years later. I mean, I haven't done a triple integral since the last time I taught this course. But I thought, I'm just going to dive in and see if it works. See if it works to just do what I tell people, which is to go to my review sheets, which I thought about carefully at the time, and follow the advice. Several things in there. If you ever find yourself in a situation where a variable has escaped its scope, there's something wrong. What I mean by that is if there were a y up here, it will escape out to here. So some comments, there can only be y's and x's here, and there can only be x's here. If that doesn't happen, you know something's wrong. Okay, flip it. You could do it in terms of y instead. If I do it in terms of y, the biggest and smallest y can be is 0 to 4. Based off of y, where do I walk out to? Well, I walk from here to here. That's from x equals 1 to x equals this. So x equals 1. And so it seems magical, and students get really mixed up by this, but it's not. It's actually simple. It just requires organized thinking. Now, I've learned that organized thinking is a challenge for people, but it's something you can practice. Okay. So I hope you're with me there. Inner bound, outer bound. That's it. So that's how I think about it, is I just make a choice for the inside. There is, the best choice for the inside, to me, that's a harder thing to point out to people. Sometimes just looking at the equations, though, you can go, well, there's only 2 equations that have a z. And the problem said above and below, so that kind of suggested something. Okay. Then I'll check all these at the end. Again, I haven't done this in years. This is the first time I've done this since when I taught this course in 2013. But I believe in this organized thinking. Okay, let's try a different one. So what else could we do? Let's do it. I only see 2 y's. Let's try y. Okay, so we have y equals 0 to y equals 6 minus 2x. And I know in the range of numbers we've been looking at, that's always positive. So I go, okay, I can do it in terms of y. Now, what do I usually call that? I think I would call that left-right, because usually when we draw the coordinate plane in our calculus book, it's written like this. So now I'm going to think about it as there's something on the left and there's something on the right, and I'm going to find the volume between them. But you don't have to let that confuse you. You say 0 to 6 minus 2x dy. You have your function. And the way you're using this is you're trying to measure something, whether it's the average temperature in a room, the center of mass for a 3D object. This function will depend on what you're measuring. Maybe it's mass, maybe it's charge, maybe it's temperature. Okay. Now we need to draw the region. It's going to be different now, though, because the remaining variables are x and z. So you go x, z. And now we're going to play the same game. So everywhere there's an x or z, we're going to graph the corresponding curve. Okay, so what do we need? We need x equals 1. There's that. Great. We need, not y equals 0. Where do we have that? We'll do we need to draw z equals the square root of x. That's going to look like this. Here we go up. Z equals the square root of x. We need to draw z equals 0. And now's when I have to be a little careful. X equals 1. I want to make sure I have the right region. Now you might say, isn't it this region over here? Well, I'm not sure, especially based off of this other things I've done. And we've already talked about the intersections and how x goes from 1 to 3. So now I understand in my process why I say do all the intersections first. because this would make you realize that you're not on this side. X is going out to 3. X's ranges from 1 to 3. We know that from the other setup. So I guess I should have said that better. So there you go. That's the inexperience of having not done it in 11 years. It's this region over here. You say, well, where is that 3 coming from? That's coming from all those intersections I should have found if I'd have been following my advice. And my advice is the intersections are y equals 4, x equals 3. Yeah, I guess those are the main intersections to think about. The other one was z equals 1. So there's a little bit of confusion there about that piece. Now, here's where things I think become a little interesting, because that particular region, if I make it look a little bigger, is not nice to do both ways. So look at that region and ask yourself your Math 126 question. Would you rather do it in terms of x, or would you rather do it in terms of y? I'd much rather do it in terms of x, because there's a clear top and bottom the whole way. So based off of x, 0 is the bottom, the top is the square root of x. So that lends itself nicely to a setup. 0 to the square root of x, 0 to 6 minus 2x. And I think those were the 3 easiest ways to do it. dy. At this point, if you're stuck, you can think about the fact that, oh, there's an x there. It's going to have to be dz dx. And this is a lot to think about. Students always struggle with this. What's kind of fun, I don't know, fun, but you could just put a 1 as the integrand and calculate all 3 of those and see if they're the same. You might not have time for that on a test. Okay, if you want to do this in terms of y, then we've fallen into one of these situations from Math 126. I think I drew that kind of inaccurately, but this is 1. This is 3. If you want to do it in terms of y, you're going to need a different pattern here than if you're up here. And that's unfortunate. So you would have to break things up. In terms of z, I should say. Okay. I think what I'll do at this point, because I think the video's gotten pretty long, and because I fumbled a little bit there, but mostly I wanted to show you how you could use my resources to study. Let's see if we've matched up. I think so. That's what I got. And you can see the method. So you can see, and typically in my resources, I try to do overkill. I try to give you every way. So I chose the inside, I drew it in 2D. I chose the inside, I drew it in 2D. Let's do another one. Only 2 bounds involve y, so dy may also be a good choice. Same things I said. I did some intersection. I did have to realize it was over here. That did require you think a little bit about what it was. We talked about that. And then just like I said, here's what you get. Chose this for the inside. Here's what you got in 2D. Here is the issue here is that things change. That's a 2D issue. Right? From there to there, it's between 1 and 3. And you can see that. 1 to 3. 1 to 3. I said it backwards. And then for here, you're between those 2 functions. So lastly, what if you chose x? I said, well, it's a bad choice, but I'll do it anyways. So you might wonder how I got these equations. And this was a lot of work. I remember when I did this. And I got those equations by combining the starting equations to try to get x by itself. So I said, well, x is equal to 6 minus y over 2. And x is also equal to z squared. And so I said, okay, we're between those things. But there's a problem with the graph, and I'll show you the graph to finish this off, is where do they intersect, and are we always between those 2 things? So that was the issue. I gave those answers, but I'm going to finish with some visuals of this. All we were doing was finding that. Okay? We first did top and bottom. So we just looked at the top and bottom. And you know, you're not guaranteed that a 3D object has a nice top and bottom, but this one did. And then we did in terms of X, and we did in terms of Y. That's the same stuff from Math 126. So we looked at these things, those cross sections, that's what we were describing. We said based off of X, Y goes from there to there. Okay, then we did this one. Based off of Y, X goes from here to here. That was our first two integrals. We described what was happening. Okay, then we said, well, let's do it in terms of, we used Y. So we said Y is always between purple on this side, and not green, and orange on this side. Ooh, that's actually in terms X in terms of Y. That's the one that's troublesome. You can see why it's troublesome here, because when you go left and right this way across the 3D object, sometimes it's gray to purple, sometimes it's orange to purple. So that was troublesome. So here is a surface where you really would not want to do it this way, because you're going to have to split things up. It is possible, and that's what I did, but I would much rather do it either in terms of top-bottom or in terms of purple-green. So let's get rid of everything else. Purple-green works because you're always between those two. In general, that's harder to see, yes. That's the one that I said, oh, I only have 2 equations for Y. 3 equations for X. Okay. So anyways, I don't know if that's helping or not, but I think it's good to get some of these visuals. It's not always going to be nice, but my steps are going to give you some good ideas of what to do. And then just a comment about this other side that I mentioned in our discussion. What happens here is you can't use the same pattern, as you can see. The pattern is correct all the way up to there, but then not correct anymore. So I hope that illustrates a few things. I feel like that's not enough. You need more examples. And so I have 3 more examples in my practice problems. I have solutions. I feel like if I rewrote those solutions, I'd clean them up a little bit, but the content is still good. I talk about thought process. So that gives you a lot of things to work from. You know, the other thing is you can scroll through here and see other quizzes. What I used to do is post things in the announcements. This was my only website, so students read the announcements. Now it's kind of a bygone way of doing things. But as you go through, you're going to see plenty of things that help you here. Exam 1 solutions from that quarter. Visualizations, line integral test prep. So although I may not be able to help you in terms of making lots of videos for 224, there's going to be something here to help you throughout the term. Okay, hope you found that interesting. Maybe I'll share this with the video, and I appreciate you